Hi everyone, welcome to goclasses. In this lecture, we will study relations closures. We will study reflexive closure of relations and symmetric closure of relations. In the next lecture, we will study transitive closure of relations. Also, in this lecture, we are going to solve all the possible questions on relations closures. Okay, some various different types of closures also we will see, which are non-standard. Reflexive closure, symmetric closure, these are standard, but some extra closures also we will see. Okay, so let's start now. This is going to be a very interesting lecture. You can take your copy pen for better understanding. Okay, let me tell you that goclasses discrete mathematics course, this is free for everyone. So on YouTube you can search goclasses discrete mathematics. This playlist you will see, and this playlist contains discrete mathematics, all compact lectures, revision playlist, gate PYQs, practice. So basically, it has everything. Okay, so you can search on YouTube. You can search Go Classes Discrete Mathematics, or on the Go Classes website, on the Go Classes app, you can find Discrete Mathematics course, Discrete Mathematics main course, as well as Discrete Mathematics compact course. Both you can find on the Go Classes website or app, or you can find this playlist on YouTube. You can search Go Classes Discrete Mathematics on YouTube. Okay, so let's see what is the content of this lecture. What are we going to study in this lecture? So we will see relations closures idea and definition. Okay, so closure of relations, what is the idea, what is the definition, what is the informal definition, formal definition. So two type of definitions we will see. We will also see reflexive closure, symmetric closure, how to find them. We will see a note on anti-symmetric closure, irreflexive closure. Okay, a note about anti-symmetric and irreflexive closure also we will see. We will also see some new type of closures and all the practice questions we are going to solve. So these four things we are going to do in this lecture. Okay, and in the next lecture we will study transitive closure, theorems, proof, and practice. Okay, so the first four things we are going to study, we are going to see in this lecture. So let's start. Let's see what is relations closures. Closure of a relation, what is the idea, what is the definition, what is the informal definition, what is the formal definition, and let's do a lot of practice. So let's see. First we are going to see informal definition, then we will see formal definition. Let me tell you, you can solve all the questions using informal definition. Also you can solve all the questions using formal definition. Okay, but informal definition, this definition you can use to solve the questions, and the formal definition you can use if some true false question comes based on formal definition, then you can use it. But to solve all the questions we are going to use the informal idea. Okay, so let's see closure of relations, what is the informal idea to solve all the questions. Okay, so let me tell you what is this concept, closure of relations. What is this concept? Let me tell you, in this concept basically two things are given to us. One is the relation on a set A is the base set on which R is a relation that is defined. So basically a relation is given to us, also a property is given to us. This property can be anything, for example reflexive, symmetric, transitive, anti-symmetric, irreflexive. This can be any property of relations. Okay, so these two things are given to us. I hope you are getting the point. So two things will be given to us. These are given to us means a relation is given, a relation and a property. Two things are given. For example, they can give you a relation and they can give you reflexive property. So relation comma property, these two things are given. And remember one more thing, that the given relation may or may not have this property P. The property P that is given to you and the relation that is given to you. So this relation may or may not have this property P. Okay. So what is the definition of, what is the idea of closure of relation R with respect to this property P? Okay. So let's see. Closure of R means closure of this relation R that is given to you. closure of R with respect to this property P. What is the definition? The definition is very simple. Let's see. This is the definition you can see. In the relation R, because the relation R may or may not have this property P, right? So what we do, in this relation R, we add minimum number of necessary ordered pairs. Remember, in a relation, every element is an ordered pair. Yes or no? In a relation, if you see in a relation, every element is a ordered pair. Correct? Okay, every element is a ordered pair, like this type of ordered pair. Okay, so every element is a ordered pair. Now, what we are saying? We are saying that closure of relation R with respect to property P is defined like this: that you what you do, you add minimum number of necessary pairs in R to obtain property P. That's it. The new relation that you will get, that is called closure of R with respect to property P. That's it. This is the definition, nothing else. But here, what are the important words? You must focus on these important words if you want to solve all the questions, if you don't want to make any mistake in any question. Okay. So remember, the relation is given to you, the property is given to you, the given relation may or may not have this property P. Now the question will ask you to find the closure of relation with respect to this property. Then what you will do, in the relation R, you will add minimum number of necessary pairs, minimum number of necessary ordered pairs you will add in R to obtain property P. Okay, these are the important words that you need to add. You don't need to subtract. You cannot subtract. You cannot remove an ordered pair. From this relation R, you cannot remove any ordered pair. Please understand. You must add. You must not remove. So you must add minimum number of necessary pairs you must add. Only the necessary pair, minimum number of necessary pairs you must add, such that we obtain this property P. Our purpose is to obtain the property P. Because the given relation may or may not have this property P, our purpose is to obtain this property P by adding minimum number of necessary pairs. That's it. These are the three important words. We want to obtain property P by adding, not by removing, by adding minimum number of necessary pairs. We want to add necessary pairs. Okay. Now, this new relation that you will get, that will be called closure of R with respect to property P. That's it. This is the informal idea. Very simple. This is actually very, very easy. With example, it will become more clear. But this is very simple, that in the relation R, you add minimum number of necessary pairs to obtain the property P. That's it. Okay. This new relation that you will get, that will be called closure of R with respect to property P. Okay. Also, let me tell you a note that for certain R comma P, because two things are given, a relation is given, property is given. So for certain R comma P, for certain combination of relation comma property, this may not be possible, means this closure may not exist. Okay, it may be possible that closure does not exist. Okay, we will see examples later. I hope you understood. Now, the definition we have seen, but maybe you got it, maybe you did not get, don't worry. Okay, now what we are going to do, we are going to do a lot of practice. Okay, but before that, let's visualize this definition. Okay, let me make a diagram to visualize this definition. So you can see closure of relation R with respect to property P. So you have this relation R. Let me say that this is the relation R. Okay, this is the relation R. And remember, this relation R may or may not satisfy this property P. Okay, this is given to you. Relation is given, property P is given. So what we do in this relation R, if this relation does not satisfy the property P, then our purpose is to obtain the property P. We want to obtain property P. Now, to obtain property P, what we need to do? We need to add only the necessary pairs in R. Okay, so what we will do? In this relation R, we will add, not remove. We will add. This is the first thing. Okay, we will add minimum number of focus on this word necessary. Only the necessary pairs we will add. Only the necessary minimum number of necessary pairs we are going to add. Okay. So add minimum number of necessary pairs. And what should happen? We are adding minimum number of necessary pairs, but what should happen? Overall, this new thing, this new relation, this must satisfy property P. Okay. So what should happen? This new relation, let's call it new relation. Let's call it new relation S. But remember, this new relation S, this must satisfy property P. Okay. So what should happen? This must satisfy, must have property P. Okay. This must have property P. I hope you understood. So very simple. In the relation R, you add minimum number of necessary pairs such that we obtain the property P. This new relation will be called closure of R with respect to property P. Okay. So this new relation S, here I can say overall I can say, from here I can say that this new relation S is called closure of R with respect to property P. Okay, that's it. I hope you understood. Now let's see some examples. Consider this example. Back to back, a lot of examples I am going to take. Okay. Consider this example. The relation R is given to you. This is the relation R. You can see in a relation, every element is an ordered pair. So total, how many elements we have in this relation R? Total 4 elements we have. In a relation, every element is always an ordered pair. Okay. So we have this relation on set 1, 2, 3. So this is the base set on which this relation R is defined. So this is the relation R which contains total 4 elements, or I can say 4 pairs, 4 ordered pairs. And this property is given reflexive. So relation is given, property is given. Two things are given to you. Now we need to find the closure of R with respect to P. Means we need to find the closure of R with respect to reflexive property. Means we need to find the reflexive closure of R. Okay, in one word I can say that we need to find the reflexive closure of R. Here please understand, R is the relation, reflexive is the property. So we need to find reflexive closure of R. Okay, means we need to find closure of R with respect to reflexive property. Okay, tell me one thing. This relation R, does it satisfy reflexive property already? If this relation R already satisfies reflexive property, then we don't need to add anything. Yes or no? Do you agree with me? If the relation R already satisfies the reflexive property, then we don't need to add anything, because we are basically adding minimum number of necessary pairs to obtain the property. But if the relation already has the property, then we don't need to add anything to the relation to find the closure. Yes or no? So tell me, this relation R, does it already satisfy reflexive property? The answer is no. Okay, because to satisfy the reflexive property, the relation must contain all the reflexive pairs. But here we have 1, 1, we don't have 2, 2, we don't have 3, 3. Okay, this is the base set 1, 2, 3. Okay, so you tell me in this relation R, which necessary pairs I must add to obtain this property? Which necessary pairs I must add? So this new relation S, okay, this new relation S, this is basically R plus minimum number of necessary pairs. Minimum number of necessary pairs. Okay. This S, this is R plus minimum number of necessary pairs, such that overall satisfies reflexive property. Okay. A simple question I'm asking. Do you agree with me that because I'm adding, I cannot remove? So all these 4 I must put. Okay. Without looking at anything, you just directly put these 4, because remember, you need to add. You cannot remove any pair. Okay. These you put. Okay. Tell me one thing now. Do you agree that whatever happens, it's necessary that I must put 2 2. If I want reflexive property, it's mandatory that I put 2 2. Do you agree? Everyone agrees? Whatever happens, whatever happens, if I want to satisfy reflexive property, then I must add 2 2. But tell me, is it enough? Is it enough? No, it is not enough, because right now this is not reflexive. Means reflexive property is not satisfied. We want to satisfy reflexive property by adding minimum number of necessary pairs. So I can say that whatever happens, 3 3 also I must add. Do you agree? Okay. Now tell me, something else should I add, or is it enough? Minimum number of necessary pairs I have added, and now you can notice that this S satisfies the reflexive property. Okay, so don't add anything else, because remember, minimum number of necessary pairs we want to add, and these are necessary pairs. Whatever happens, I must add these two. These are necessary pairs, and that's it. Minimum number of necessary pairs I have added, and now this S satisfies reflexive property. So this S is reflexive closure of the given relation R. That's it. This is the answer. Okay. So what is this S? This is the reflexive closure of given relation R. That's it. This is the answer. I hope you understood. Tell me the answer for this question. The relation is given to you, and the property is symmetric property. Find the closure of R with respect to this symmetric property. Means find symmetric closure of R. Here, please understand, R is the relation and symmetric is the property. So we need to find the closure of R with respect to symmetric property. Tell me one thing, this relation, does it already satisfy symmetric property? This relation, does it already satisfy symmetric property? Because if this relation already satisfies symmetric property, then we don't need to add anything. Okay, then there is no need to add anything, and we can directly say that R is symmetric closure of itself. But here, this R does not satisfy symmetric property. You can notice we have 3 2, but we don't have 2 3. So this does not satisfy symmetric property. Okay, so tell me again the same thing. What is S? S is the new relation, which is equal to R plus minimum number of necessary pairs. Okay, such that the symmetric property we must obtain. So one thing you agree with me, that in this relation I need to add some pairs, minimum number of necessary pairs I must add, so that symmetric property is satisfied. Whatever happens, you agree with me that 2 3 I must add. Okay, yes or no? All these pairs you must put as it is, because you cannot remove anything. We cannot remove any pair. Okay, now you agree with me that if I want symmetric property, there is a mandatory thing. What is that? I must add this pair. Okay, this is mandatory. And now you check. This is mandatory, I have added. So this is necessary pair I have added. And now can you notice that after adding this necessary pair, symmetric property satisfies. So I can stop here. This was necessary. This was necessary to add. And now after adding the necessary pair, symmetric property holds. So I can stop. Okay, minimum number of necessary pairs I have added, such that symmetric property satisfies. So I can stop, and I can say that this S is what? This S is symmetric. This S is symmetric closure of R. Okay, that's it. This is the answer. I hope you understood. Very simple. Tell me the answer for this question. The property is irreflexive, and this is the given relation. Find the closure of relation with respect to this property. Means you find the irreflexive closure of R. Irreflexive is the property, R is the relation. We need to find the closure of relation with respect to irreflexive property. First, you tell me, the given relation, does it already satisfy this property? Because if the given relation already satisfies this property, then I don't need to add anything. I can directly say that the relation is its own closure with respect to this property. Okay, tell me, the given relation, does it already satisfy the property irreflexive? No, this does not satisfy irreflexive property, because irreflexive means what? Irreflexive means there should be no reflexive pair, but here we have reflexive pair 1 1. Okay, so this given relation is not irreflexive, correct? Okay, so you can see this given relation, this is not irreflexive. Now something interesting, can you add something to this relation such that you can bring this property irreflexive? Is it possible? Remember, you cannot remove. Again and again I am telling, some students are saying in the chat, some students are saying remove 1 1. Please don't say that. Tell me one thing, in this relation R, can I add some pairs? Can I add something so that I can bring this property irreflexive? No, it can never happen. Yes or no? So I can say irreflexive closure of R does not exist. Okay, do you agree with me? Because remember, if I write as, okay, whatever I add here, 1 2 2 1 3 2. Okay, basically what I am saying, if I add anything here, whatever you add, this will never be satisfying irreflexive property. Okay, see, very simple point. This is not irreflexive. This is not irreflexive. And one more thing, remember, if I make a new relation such that that is r plus some pairs, some necessary pairs, or basically some r plus something. So tell me, if I do r plus something, I can never satisfy this irreflexive property by adding something to this relation R. Okay, so this can never satisfy, this can never satisfy irreflexive property. Okay, by adding something to this relation R, because this relation R already contains 1 1. So by adding something to this relation R, we can never bring the irreflexive property. So this irreflexive property we can never bring by adding something to this relation R. So I can say that irreflexive closure of R does not exist. Does not exist. Okay. So your answer must be does not exist. The irreflexive closure of this relation R does not exist. Do you remember I told you that for certain relation comma property pairs, the closure may not exist? This is the perfect example. For this relation and this property irreflexive, now for this pair of property comma relation, the closure does not exist. Very simple. Tell me the answer for this question. Here the property is irreflexive. In the previous question also, the property was irreflexive. Here also the property is irreflexive. Find the irreflexive closure of this relation R. Remember the definition of closure of a relation with respect to a property P. Remember the definition. What is that? That in this relation R, you add minimum number of necessary pairs. You add minimum number of necessary pairs so that we bring this property. Okay, we want to bring this property. So tell me one thing. This relation R, did you notice? This already has this property irreflexive. So if you add minimum number of necessary pairs, if you add to bring this property, then basically you don't need to add anything. This relation already has irreflexive property, so I can say I don't need to add anything. This relation is closure of itself. This relation is irreflexive closure of itself. Okay, so did you notice that this relation is already irreflexive? This is already irreflexive. Okay, so there is no need of adding anything. You can just keep this relation R as it is. This relation R already satisfies this property. So I can say find irreflexive closure of R. The answer will be what? The answer will be R itself. Okay, here the irreflexive closure exists. Remember, R itself is irreflexive closure of R. Okay, is this clear? Already irreflexive, so R itself is irreflexive closure of R. Okay, isn't it interesting? Because I told you the definition of closure of relation with respect to property P. The definition is very simple, that we want to bring this property P by adding minimum number of necessary pairs. Here the relation already satisfies this property, so there is no need of adding anything. So I can say relation R itself is irreflexive closure of R. So here the answer will be R itself. So if I ask you, irreflexive closure always exists, is this statement true or false? Irreflexive closure always exists. No, this is not true, because in the previous question, you can see in the previous relation, for this relation, irreflexive closure does not exist. And can I say irreflexive closure never exists? That is also not true, because here for this relation, irreflexive closure exists. So what is the final statement? What is the correct statement? Irreflexive closure may or may not exist. Yes or no? For some relations, irreflexive closure exists. For some relations, irreflexive closure does not exist. One more interesting thing you notice here. If the relation already satisfies irreflexive property, then irreflexive closure exists, the relation itself. But if the relation does not satisfy irreflexive property, then irreflexive closure does not exist. Okay, this interesting point I hope you can observe. At the end also, I will come back to this point, so you don't have to write it right now. I will come back to this point, but you can make this observation, that if the given relation does not satisfy irreflexive property, then irreflexive closure does not exist. And if the given relation already satisfies the irreflexive property, then this relation is irreflexive closure of itself. Simple, very simple. I hope you understood the concept. Now I want correct answer from you for the next question. Tell me the answer for this question. The relation is given to you. This is the relation which has how many elements? In the relation, how many elements we have? 1, 2, 3, 4. 4 elements are there. In every relation, every element is ordered pair. So basically, these are the 4 elements. So what is the cardinality of R? That is 4. That is even number. Now the property is given to you. Has odd number of elements. This is the relation given. This is the property given. Notice that this is a new property. Something new has been defined. Similarly, in the GATE exam, something new they can define. Okay. So tell me, this relation and this property, the property has an odd number of elements. This property we want to satisfy. We want odd number of elements in the relation. Right now, remember, this relation does not satisfy this property. Do you notice? This property P is not satisfied by this relation R. So what we need to do? If you want to find closure of R with respect to this property P, then what you need to do? In this relation R, you need to add minimum number of necessary pairs to satisfy this property P. Okay. So one thing is clear. If I want to satisfy this property P by adding something, by adding minimum number of pairs in this relation R, only one pair I need to add. That's clear, right? That is clear that I need to add one pair. So adding one pair is clear to us. But which pair will you add? Is there any pair which is necessary? If some student is giving answer by adding some pair, then you are not focusing on the word necessary. Is there any pair? One pair I need to add, that I know, but is there any one pair which is necessary to add? Necessary word, focus on the necessary word. Tell me, is there any pair which is necessary to add here to bring this property? Let me tell you. See, notice one thing. I need to find a new relation which is R plus minimum number of necessary pairs. Minimum number of necessary pairs I need to add so that this new relation satisfies property P. Satisfies property P. Now, you know that to satisfy this property P, that is having odd number of elements, and this relation R contains even number of elements. So, how many minimum pairs I need to add? One pair. But which pair is necessary? Maybe some student, what they can do? Maybe some students will do R union, means in this R, they will add, which pair they will add? They can add maybe 1, 3. Some student will add 1, 3. Okay. Now you can notice that we have added minimum number of pairs and the property is satisfied. But which word is missing here? Do you notice? Minimum number of pairs we have added such that property P is satisfied. Minimum number of pairs added, property P satisfied. These three words are okay. But which word you are missing? Necessary word. Was it necessary to add this pair? Was it necessary? No, it was not necessary, because maybe some other student, what they can do, what some other student can do, some other student will do like this, 3, 3 they will add. Okay. So you can notice adding 1, 3, adding this pair is not necessary. Adding this pair is also not necessary because you can add this pair. Maybe some student will add something else. Maybe some student will say, sir, I will add 2, 2, or maybe I will add 2, 3. Okay, and so on. I hope you are getting my point. That answer will be this closure does not exist. That will be the answer. I hope you understood. Okay. So remember, the final answer will be what? The final answer will be what? The final answer is, for this relation R with respect to this property P, closure does not exist. Okay. So the final answer is closure of R with respect to P does not exist. Okay. Now is it clear? Whatever question comes in the GATE exam, anything new they define, can you solve? Let me know. Are you confident now? Okay. So you can see this necessary word here is violated. Okay. I hope you understood. So all these words are important. Remember, this necessary word is important. Necessary pairs I need to add. Actually, there is no necessary pair here to satisfy this property. There is no necessary pair. Minimum number of necessary pairs we need to add to satisfy this property P. Okay, all these things are important. I hope this particular point is clear. Okay. Tell me the answer for this question now. I have taken all the variations, remember, so that any question comes in the GATE exam, you should be able to handle it. The relation is given to you and the property has odd number of elements. Now you find the closure of this relation R with respect to this property P. Notice one thing, this relation already satisfies this property P. This relation already satisfies This relation already satisfies property P. So because this relation already satisfies property P, there is no need of adding anything. Already satisfies property P, so there is no need to add anything to obtain property P. To obtain property P. Okay, agree with me that because this relation already satisfies property P, so there is no need to add anything. There is no need to add any pair in this relation R to obtain property P. So what will be closure of R with respect to property P? The answer will be R itself. Okay, very simple. The answer will be R itself is the closure of R with respect to property P. Okay, simple. Tell me the answer for this question now. The property P is not reflexive. The relation is given to you and the property is not reflexive. We want to satisfy this property that the relation should not be reflexive. Find closure of R with respect to property P. Pause the video, try this question. This is a good, interesting question, and then play the video. This relation R, notice one thing, this already satisfies the property P because this relation is not reflexive. The property is not reflexive. And this relation already has this property that it is not reflexive. You can see it has 1 1, but it does not have 2 2, it does not have 3 3. So this relation already has this property P. So this relation, you can see, already satisfies property P. And because it already satisfies property P, so there is no need to add anything. There is no need to add any pair to obtain property P. Okay, so I can say that closure of R with respect to P, this will be R itself. This will be R itself. Okay, very simple, right? I hope you understood this. Tell me one more thing. Is not reflexive, is it same as irreflexive? Are these two things same? Tell me. Like, look at these things. The first property is reflexive. The second property is irreflexive. The third property is not reflexive. And fourth property is not irreflexive. Are they same? Is not irreflexive. What is the difference in all of them? Is there any difference here? All of them are different. All of them are actually different. All are different. All these are different properties. Yes or no? Why these are different properties? Can you give me an example where I can say that all these are different properties? For example, assume that we have a base set 1 2 3. This is the base set. Now notice, if I write this relation 1 1 2 2 3 3, you can notice this relation is reflexive. This particular relation satisfies which properties? Tell me. This particular relation satisfies the property 1. This does not satisfy property 2. Is not reflexive. This does not satisfy property 3. Is not irreflexive. This satisfies property 4. Okay. Now, another example, let me give you. Consider this relation R2. Consider relation R2, that is 1 1 2. Okay, this relation satisfies which properties? Which four properties? You can see this does not satisfy property 1. Property 1 is not satisfied. Property 2 satisfied. Is not reflexive. Property 3 satisfied. Is not irreflexive. Property 4 not satisfied. Okay, let me give you another example. R3. Consider R3, that is 1 1 1 2. Now notice this satisfies what? This relation. You can see this relation does not satisfy property 1. This does not satisfy property 2 also. It is not reflexive, it is not irreflexive. Reflexive means must contain all the reflexive pairs. Irreflexive means must not contain any reflexive pair. Means reflexive means containing all reflexive pair. Irreflexive means containing no reflexive pair. And you can see this relation, does it satisfy property 3? Is not reflexive. Yes, property 3 satisfied. Property 4 is not irreflexive. Yes, property 4 satisfied. Okay, I hope you are getting the point. So like this, all these are actually different properties. Please understand. Okay, like this you can make more examples, you can make, and you can check that these four are different properties. Okay, so very simple. Tell me the answer for this question. The property is not reflexive. We want a relation which is not reflexive. This relation R is given to us. Find closure of relation with respect to property P. This relation, does it satisfy this given property? This is the property is not reflexive, but actually this is reflexive. The relation is reflexive because this is the base set 1 to 3 and all the reflexive pairs are there. So the relation R, this does not satisfy property P. Yes or no? Property P is not reflexive, but actually this is reflexive. So this does not satisfy property P. Now you tell me, can you add something to R to bring this property P? This relation is already reflexive. Can I add something and make it not reflexive? No, that's not possible. Yes or no? So you can notice that in this relation R, can I add something? R plus something. R plus something. Can I add something so that this property I can bring? No. Yes or no? Can never satisfy P. Can never satisfy property P. So finally I can say that the closure of R with respect to this property P, that closure does not exist. Closure does not exist. Okay, is this point clear? Very simple. I hope you understood. One more note I want to tell you. One more note. Remember, closure, if exist, is always unique. Never say that there are multiple closures. Okay, please understand that for any relation, let me write this note here. For any relation R, comma property P, for any relation R, comma property P, closure of R with respect to P, closure of R with respect to P, either it will not exist, or if it exists, then it will be unique. Okay, so remember, either not exist, okay, either not exists, or if exists, then it will be unique. If exists, then always unique. Then always unique. Okay, so never say that there are multiple closures. Okay, don't use this word multiple closures. Is this clear? So I can say, so never say multiple closures. Exist. Okay, never say that multiple closures exist. Multiple closures Okay, is this point clear? I hope you understood. Very simple. So the closure of any relation with respect to any property, either it does not exist, or if it exists, then it will always be unique. Okay, so never say that multiple closures exist. Multiple closures will never exist. Okay, either the closure does not exist or it exists. If it exists, then it will be unique. Tell me the answer for this question. The property is anti-symmetric property, and this is the given relation. We need to find the anti-symmetric closure of R. Means for this relation R, we need to find the anti-symmetric closure. Closure of relation R with respect to anti-symmetric property we need to find. This relation, does it already satisfy this property anti-symmetric? No, this does not satisfy anti-symmetric property, right? Yes or no? This is not anti-symmetric. This relation is already not anti-symmetric. Why it is not anti-symmetric? Because you can see we have 1 2, we have 2 1. Okay, so tell me one thing. Can I add something and bring this anti-symmetric property? Tell me, in this R, can I add something? R plus something. R plus something. Can I ever bring this anti-symmetric property by adding something to R? No. By adding something to R, this violation will never be gone. This is the violation of anti-symmetric property. This will never be gone by adding something. So I can say that R plus something will never never satisfies anti-symmetric property. Okay, I hope you understood. So finally I can say anti-symmetric closure of R, that does not exist. The answer will be does not exist. Okay, I hope you have become expert now. Are you feeling more and more confidence now? Very easily we are checking. Tell me the answer for this question. Anti-symmetric property, the relation is given to us. This relation, does it already satisfy anti-symmetric property? Yes, this relation is already anti-symmetric. This relation is already anti-symmetric. So if this relation is already anti-symmetric, then there is no need to add anything to bring this anti-symmetric property, right? Okay, so I can say anti-symmetric closure of R, that will be R itself. So this is the answer. So here the anti-symmetric closure exists, and R itself is the anti-symmetric closure of R. Okay, so I can say that R itself is anti-symmetric closure of R. Okay, that's it. Very simple. I hope you understood. So that's it. We have seen the informal definition and we have done a variety of questions. And I hope you are feeling confidence now. I told you that using the informal definition, using the informal idea, we will be solving all the questions. And I promise you that in the GATE exam, whatever question comes, whatever new property they define, whatever relation they give you, using this informal definition, using this informal idea, you can handle any type of question. Okay. So this is the slide that we have already seen. You already know the informal definition. Closure of a relation with respect to a property P. Two things are given to us. A relation is given to you, a property is given to you. And remember, the original relation may or may not satisfy this property P. Okay. So here, the closure of this relation with respect to this property P, that is defined like this, that you add minimum number of necessary pairs to obtain this property P. The new relation that you will get, that will be called closure of R with respect to property P. And notice one thing, that for certain R comma P, for certain pairs of relation comma property, the closure of relation with respect to that property may not exist. Okay. So we have seen the examples also. I hope you understood. Now, this was our content of this lecture. And now notice one thing, what we have covered so far. We did not even see the formal definition. without looking at the formal definition. So far, what we have covered now, we have covered relation closure idea and definition. We have covered, we have seen reflexive closure, symmetric closure. We have seen a note about anti-symmetric closure. We have seen irreflexive closure. We have seen different type of closure, new type of closure also. Some new properties we have taken, and we have seen all the practice questions. So these four that we wanted to cover in this lecture, we have already covered. All these are already covered. Okay, but still, what we need to do? We need to see the formal definition, because in the GATE exam, they can ask you some true-false questions based on the formal definition. Now we will see relation closures, formal definition, and using the formal definition, we will solve all the questions that we have already solved. This formal definition will be very useful in the true-false questions, in some theoretical conceptual question where they are asking the formal definition, or where they are giving the formal definition in the question. There, this definition will be helpful. But remember, in the remaining questions where relation is given, property is given, then you can just use the previous definition, that was informal definition. You can just use that. Now let's see the formal definition of relations closure. So let's see the formal definition. What is given to us? A relation is given, a property is given, and remember, this relation may or may not satisfy this property P. Okay. So now what is the formal definition? Closure of relation R with respect to this property P. The formal definition is like this. You will not understand this in the first time, but when I make a diagram, then you will easily understand this. Okay. So notice that what is closure of relation with respect to property P? If there is a relation S with property P containing R, means remember one thing, closure of relation R with respect to property P, that is a new relation. Do you agree with me? When you find closure of R with respect to property P, then that closure is basically a new relation. That new relation may or may not be same as R. We have already seen. Okay. So closure of relation R with respect to property P, that is a new relation S. So you can say if there is a relation S which has this property and which contains R, such that this S, this is subset of every relation with property P that contains R, then S will be called closure of R with respect to property P. Very interesting definition, this formal definition. So I think you did not understand. Now let me explain. Let me make a diagram to explain this. So what is closure of R with respect to property P formal definition? It's like this, that you have this relation R. Notice, if this relation R already satisfies property P, then R will be closure of itself, that we already know. Okay, so first let me write a note that if R already satisfies property P, then what I can say, then I can say that R is the closure of itself with respect to property P. R is the closure of itself with respect to property P. Okay, so that we already know. Now let's understand this formal definition now. So we have this relation R. This is the relation R. Let me make like this box, this circle. So this is R. Okay, these are the elements, means every element is an ordered pair, that we already know. So this is the relation R. Okay, now remember, this relation R, it may or may not satisfy property P, that we already know. If this R satisfies property P already, then R will be closure of itself with respect to property P, that we already know. But tell me, if R does not satisfy property P, then how to find the closure of R with respect to property P? Tell me. What we will do? We will add minimum number of necessary pairs to obtain this property P. Do you agree with me? Okay. So if this relation R does not satisfy property P, then how to obtain closure of R with respect to this property, what I will do? I will add something to R. Okay. But remember, I will add minimum number of necessary pairs only. I will be adding only the necessary pairs. It's like this, that I will be adding the necessary pairs only. Okay, so let's assume that these are the necessary pairs that I've added. Okay, please understand these pink. What are these pink ones? These are the necessary pairs that I have added. These pink ones. These, or maybe let me do one thing, that let me put yellow here. What are these yellow dots? These are the minimum number of necessary pairs. These are the minimum number of necessary pairs. Okay, minimum number of necessary pairs I am adding, so that this new relation S, this is the new relation S. This new relation S satisfies property P. Okay. Now, something interesting. You tell me, these are just these yellow ones. These are just the necessary pairs, minimum number of necessary pairs. If these are necessary pairs, and if I want to create a superset of R which satisfies property P, and these are already the necessary pairs, then tell me, do you agree with me that if I create any superset of R which satisfies property P, then that will definitely be superset of S? Did you understand this point that I'm making? Notice, so far this is perfect. You can see, so far we have used the previous definition. We have this relation R. If this relation R does not satisfy the property P, then what we will do? To find the closure of R with respect to this property P, what I will do? I will add minimum number of necessary pairs, and I will get this new relation S. This new relation S satisfies the property P. Okay, that is perfect, no problem. Tell me one thing. Remember, these yellow ones, these are the necessary pairs. So if I make any superset of R which satisfies property P, will it definitely have these necessary pairs? If I make superset of R which satisfies property P, any superset I make, any superset of R I make which satisfies property P, then is it necessary that these necessary pairs will be there? Yes, because these are necessary pairs. So of course, if these are necessary, then they will definitely be there. Okay, yes or no? So I am saying that if you create any superset of R which satisfies property P, then that will definitely contain these necessary pairs. It can have something extra, it can have, but the point is it will be a superset of S, because S contains minimum number of necessary pairs. And this any superset of R which satisfies property P, it will be a superset of S. Okay, any I can say that any superset of R which satisfies property P will be superset of S, because in this S we are adding minimum number of necessary pairs. I hope you got this point. Okay, so remember, let's call this T, and let's call this M. Okay, overall I am saying that this STM, they satisfy property P. Please understand, STM, they satisfy property P. They satisfy property P, and they are super, and they contain R. And they contain R. Okay. But remember, S is the closure. This S is the closure. This S is the closure of R with respect to P. So I can say that this closure is basically subset of M comma T. Okay, so I can say that this S will be subset of M. This S will be subset of T. Okay, I hope you understood. If you did not understand, then just read this statement again. You can see closure of R with respect to property P. The formal definition is like this, that if this relation does not satisfy the property P, then what we will do? Then we will create a new relation. That new relation is S. We will create a new relation which satisfies property P and which contains R, because In this relation R, we will add something. We will add minimum number of necessary pairs we will add. So we are adding something. So this relation S, this new relation S, which is the closure, it will contain R and it will satisfy property P. But there is one more condition, that is this S will be subset of every relation which contains R and which satisfies property P. This S, this closure will be subset of every relation with property P which contains R. Then this S will be called closure of R with respect to property P. The same thing this diagram says. I hope it is clear. Okay, let me write in terms of first order logic. Okay, so let's see closure of R with respect to property P. Okay, let me write in terms of first order logic what I'm saying, this definition, this formal definition, let me write. So closure of R with respect to property P, that is a new relation S. Okay, that is a relation S. That is a relation S. And of course, this relation S, what it will do? This relation S contains R and satisfies property P. Okay, that is clear. This actually is clear from the previous definition also, from the informal definition also, that closure of R with respect to property P, that will be a new relation. We are creating a new relation by adding minimum number of necessary pairs to R to obtain this property P. So this new relation will contain R and it will satisfy property P, this new relation. Okay, but there is one more thing. This should be satisfied, this should be satisfied, and remember what should happen for all relations. I can say for all relations T. Okay, for all relations T, what should happen? This should happen that, remember, for all the relations, for all relations T, what should happen? That if this T also has these two properties, means if this T is superset of R, T contains R, and T satisfies property P, and T satisfies P, and T satisfies P, then what should happen? Okay, then what should happen? Then this S must be subset of T. Okay, then this S must be subset of T. This is the formal definition. I hope you understood. In simple words, I can say that this S is the smallest relation which satisfies property P and contains R. In simple words, if you did not understand so far, then in simple words I can say that this S is basically smallest relation which has these two properties. Okay, so I can say that, okay, let me just write one more time. Closure of relation R with respect to property P. So basically I can say, remember this definition, I can write like this, that this closure of R, that is a new relation. Okay, that is a relation S. That is a relation S. Or I can say closure of R with respect to property P, that is the smallest relation S that contains R and satisfies P. Okay, that contains R and satisfies P. To be honest, this definition has a problem. What is the problem here? Do you remember the example where we were having the property having odd number of elements? Do you remember example where the property was having odd number of elements? So If we take that property, then this definition will give you wrong answer. Okay, because you will be finding the smallest relation that contains R and satisfies property P. Then you can add any extra pair. Yes or no? Do you agree with me? You can add just one extra pair you can add. Then what will happen? It will be a smallest relation which contains R, which satisfies property P. You will be thinking that you got the answer. But there is a problem there. What is the problem? Actually, the smallest relation S. What is the meaning of smallest here? Just understand what the meaning of smallest. The meaning of smallest is what I'm going to write. The meaning of smallest is that if you can make any relation which has these two properties, then that must be a superset of S. Okay, so let me explain the meaning of smallest now. What is the meaning of smallest? The meaning of smallest is this, that for all the relations T, for all the relations T, for all the relations T, which has these two properties, then this T must be superset of S. This is the idea. Okay, this is the meaning of smallest here. So the meaning of smallest is that for all the relations T which have these two properties, what are the properties? That T contains R, means T is superset of R, and T satisfies P. Okay, so you can see for all such relations which have these two properties, then what must happen? This S must be smallest, means this S must be subset of T. This is the meaning of smallest. Now this is the perfect definition, and every question you can solve using this definition. This is the formal definition. I hope you understood this. I have tried my best to explain this formal definition to you. This is a formal definition. In the gate exam they can ask you maybe true false questions, or maybe in the question maybe they can give you this definition. So from this definition you must understand that they are talking about the closure of relation R with respect to property P. Basically this definition simply means that we are talking about closure. Okay, I hope you understood. If you did not understand, then I will take some examples, don't worry. But I hope you understood that formal definition is like this, that closure of relation R with respect to property P, that is a new relation S which contains R and which satisfies property P, such that S is subset of every relation which contains R and satisfies property P. Means S is basically the smallest, means it is the subset of every relation which has these two properties. Then I will say that S is closure of R with respect to property P. And this note you already know, that for certain R comma P pairs, for certain relation comma property pairs, the closure of relation with respect to that property may not exist. This we already know. We have already seen the example. Okay. So I hope you understood this formal definition. If you did not understand, then don't worry, just wait. Let's take some examples. Basically, all the questions, all the examples that we have already solved, let's solve using this definition. Okay, I think 8 or 10 questions we have already done using the first definition. Using our informal definition, 8 to 10 questions we solved. Let's solve all of those questions using the formal definition, so that we can understand the formal definition also. But remember, to solve the questions in the exam, we will use the first definition, the informal definition only. But right now, to understand the formal definition, I am again going to solve all these 8 to 10 questions that we have already solved. Okay, so let's see this first question. The property is reflexive and the relation is given to you, and we need to find the reflexive closure of R. So let's see here. I will use the formal definition only. So you notice one thing. This is the relation and the property is reflexive. So what is the reflexive closure of R? Reflexive closure of R, that is a set that contains R and has this property. Yes or no? Reflexive closure of R, reflexive closure of R will be a new relation. It will be a new relation. It will be a new relation S, such that what should happen? What should happen? This S must contain R. Also, what should happen? This S must satisfy property P. And what should happen? And what should happen? This S must be smallest. S must be smallest. S must be smallest among all relations which satisfy property 1 comma 2. Okay, means I can say that S must be smallest among S must be smallest among all relations with 1 comma 2. With 1 comma 2. So okay, maybe I should write in a cleaner way. So I can say that S should satisfy property P. And what should happen? The third thing is that S is smallest S is subset of, I can say S is subset of all relations with with these 1 comma 2 property. Okay, with 1 comma 2. So anyway, this is the formal definition. So tell me one thing. We want reflexive closure of R. So we want to find S. I want to find S. So tell me what will be S. S contains R. So first R I will write as it is. Okay, because S contains R. So you write this R as it is. Write it as it is. Okay. Now what we need to do? So this is clear that S contains R. Means everything that R has, S also has. So this is clear. Second thing, S must satisfy property P. Okay. So if S must satisfy this reflexive property, then I must have 2 2, I must have 3 3. Agree? Okay. Now for a moment stop and tell me. Now you tell me, if I make any relation which has 1 comma 2, if I make any relation which has this 1 comma 2, then can I say S will be subset of that relation? Please tell me, if I make any relation which is superset of R and which has reflexive property, any reflexive relation which is superset of R, if I make, can you guarantee that S will be subset of that? Yes, because if I make a reflexive relation which is superset of R, then that must contain 2 2 3 3. Something extra can be there. If I make any relation which has reflexive property and it is superset of R, then that will definitely contain 2 2 3 3. Maybe some extra things can be there, but the point is that will definitely be superset of S. This is what I am saying, that S must be subset of all the relations which have property 1 comma 2. So now you can notice that this S, this is subset of all the relations which have these two properties. So finally this S has all these three properties, and I can say that this S is the reflexive closure. Reflexive closure of R. Okay. Anyway, I know that you can easily find the reflexive closure. Okay, using the first definition, using the informal definition, I know. But my purpose, what is that? To explain the formal definition. That is my purpose. My purpose is not to find the reflexive closure, that you can easily do. But my purpose is to explain the formal definition. Is the formal definition clear? Let me know. Let's see. Let's solve this question. The property is symmetric. Now, again, the same thing. We need to find the symmetric closure of R. So if I want to find the symmetric closure of R, then that will be S. Yes or no? Symmetric closure of R will be S. What are the properties S must satisfy? S must contain R, and S must satisfy symmetry, symmetric property, or I can say property P. S satisfy property P. Okay. And third, Okay, all these things. And third, that S is a subset of all relations. S is subset of all relations that satisfy 1 comma 2. S is subset of all relations with 1 comma 2. Okay, so this type of S I need to find, this type of new relation S I need to find. So how to find this? S contains R, means R I will write as it is. S has every element that is there in R. Okay, so R, you write R as it is. Okay, I am writing R as it is. Very good. So you can see that S contains R. This is perfectly okay, done. This is done. Now S must satisfy P, but here at this moment S does not satisfy symmetric property. So S must satisfy symmetric property. So what is necessary? Adding 2 3, that is necessary. Okay, now S satisfy property P. So these two are done. Okay, the first two, these two are done. These are done. Okay, now notice one more thing. If I make any relation which is superset of R and which has symmetric property, any relation you consider, any relation you consider which is superset of R and has symmetric property, any such relation you consider, there is a guarantee that this S will be subset of that relation. Do you agree with me? If I make a relation which contains R and has symmetric property, then that relation will definitely have this pair. Maybe some extra pair can be there. The point is that relation which has these two property, then S will be subset of that relation. Means S is subset of all the relations which have these two properties. So finally I can say that S, this is the closure. Okay, because all these three properties are satisfied. So I can say that S is the symmetric closure of R. That's it. This is the answer. I hope you understood. Let's consider this example. We have this relation R and the property is irreflexive. We need to find the irreflexive closure. So if I want to find the irreflexive closure, what should happen? Irreflexive closure of R, that will be a new relation S. This new relation should have what properties? This must contain R. This must contain R. And this must satisfy property P. And the third thing is also there. The third thing is also there, that this S must be subset of every relation which has 1 comma 2. Okay, S is a subset of every relation with 1 comma 2. Okay, actually notice one thing, these two properties you cannot satisfy, the 1 comma 2, because this relation R, you can notice this is not irreflexive. This is not irreflexive. And you notice one thing, if you focus only on the first two properties, forget about the third. I know all the three must be satisfied, I know that, but you can't even satisfy the first two. You can't even make a relation which contains R and which has this irreflexive property. Basically, this 1 comma 2 itself we can never satisfy. In this relation R, if I want to satisfy the irreflexive property, okay, then I can never do that, because already you can see this violation is there. So if I add something else, if I add something else, then this violation will never be gone. So I can say that this 1 comma 2 itself we can never satisfy it. Okay, yes or no? I can say that these 1 comma 2 itself we can never satisfy. We can never satisfy. Okay, so that is the reason I can say irreflexive closure does not exist. That's it, very simple. I hope you understood. What about the answer for this question? The property is irreflexive and this is the relation. Here you can notice that this already has this property P. Okay. So we need to find the irreflexive closure of R, because this relation already satisfies this property P. So it will be irreflexive closure of itself. Okay. You can easily notice all the three properties will be satisfied because the answer will be R. What is the reason? Because you can see that R contains R. And second thing, you can notice that R already satisfies P. Okay. And the third thing, notice one thing. If any relation has these two property, then R will be subset of that. Okay, no problem. Yes or no? If any relation has these two property, then R will be subset of that, because if any relation has these two property, then it means that relation is a superset of R. So R will be subset of that. Okay, yes or no? So very easily you can see that. Very easily you can see that R is a subset of every R is subset of every relation with 1 comma 2. Okay, yes or no? So I can say that S is equal to R. I can say basically S is equal to R. I hope you understood. Okay, very easy, right? So finally, the answer will be the irreflexive closure of R. That will be R itself. Okay, so I know that now you are getting the idea of the formal definition. Just one two example, or I will take. So consider this example. This example will actually tell you the importance of the third property, right? One, two, three. Okay, the third statement. This example will tell you the value of the third statement. So the relation is given to you. In this relation, total we have 4 elements, even number of elements we have. The property is having odd number of elements. We need to find the closure of R with respect to this property P. Okay. We need to find closure of R with respect to property P. So closure of R, that is a new relation S, that you already know. So closure of R is a new relation S, such that what should happen? S must contain R. Also, what should happen? S must satisfy P. S must satisfy P. And what should happen? The third thing is very interesting now in this particular question. What should happen? That S is subset of every relation with 1 comma 2. Okay. S is subset of every relation with 1 comma 2. Now the interesting thing will come here. You notice, you can see that I want S, a new relation which contains R, so it must contain R. Okay, so maybe some student, what some student will do? Some student will create S1. Okay, what they will do? They will put 1 1. They will put 1 2. Basically, they will put R plus. Okay, so what they will do? See, some student, what they will do? They will do R plus, because S must contain R. Okay, so R must be there. S must satisfy P, having odd number of elements. So what some student can do? Student S1, what they can do? They can add this pair 1 3. So far these two are satisfied or not? The first two, just tell me simple point. 1 comma 2 are satisfied or not so far? Yes, 1 comma 2 are satisfied. You can see this 1 comma 2, these are satisfied because you can see this S1 contains R. Also, this S1 satisfies the property having odd number of elements. So far this S1 has 1 comma 2. But this S1, does it have this 3 also? Is this S1 subset of every relation with property 1 comma 2? The answer is no, because notice, I can make a new relation, I can make which will have 1 comma 2. What I can do? I can do this plus 3 3. Now notice, this S2 also has 1 comma 2. This also has 1 comma 2. This S1 also has 1 comma 2. has 1 comma 2. This also has 1 comma 2. Okay. Now tell me, this S1, is it subset of S2? No, S1 is not subset of S2 because in S2 we don't have 1 3. Is S2 subset of S1? No, because in S1 we don't have 3 3. Did you get the point? That now this third statement you cannot satisfy. Okay. Whatever you do, you can never satisfy the third statement. If you satisfy 1 comma 2, then you cannot satisfy the third statement. So finally I can say that closure does not exist. Okay, because you can easily see this S1 is not subset of S2. This S2 is not subset of S1. So basically this third statement is not satisfied. So finally for the closure I can say closure does not exist. Don't say there are multiple closures. Don't say that. Okay, don't say that this is also closure, this is also closure. I told you closure is always unique if exist. Either the closure does not exist. If exist, then it will be unique. Here the closure does not exist. The reason is because this third statement will not be satisfied whatever you do. If you satisfy the 1 comma 2, then you cannot satisfy 3. I hope now it is clear. Now you can appreciate the formal definition. I hope you understood the formal definition now. Okay. So basically what the formal definition says, that the closure of relation with respect to a property is a new relation which contains R, which satisfies P, and also this is smallest. Means what it means? It means that this is subset of every relation which has this 1 comma 2 property. Okay. So using this example, you can easily understand the value of formal definition. I hope it is clear. So we have seen informal definition, we have seen formal definition. Remember, the formal definition we are not going to use to solve the questions. To solve any question in the exam, we are going to use the first definition, informal definition. Means to find the closure of a relation with respect to some property P, what we will do? We will add minimum number of necessary pairs to obtain that property. That's it. That informal definition we will use to solve all the questions. We are never going to use the formal definition to solve any question. But the formal definition, I told you, I explained, because maybe in the gate exam some true false questions can come, or maybe in some question they can give this formal definition, and then you must understand that this formal definition actually means closure. See, in the question, what they can do, they can give you the definition without using the word closure. They can give the formal definition. They will write the formal definition, and they will not use the word closure. So from the formal definition, you must understand that they are talking about the closure. That is the reason I explained the formal definition. This type of questions I will give in the weekly quizzes. In the goclasses test series also I will put this type of question, where in the question I will define the formal definition, but I will not use the word closure. Maybe some other word I will use, or maybe just I will give this definition, formal definition, and then some question I will ask. So here what you should do, from the formal definition that is given to you, you must understand that this is the definition of closure. Once you understand that this is the definition of closure, now you can solve the questions with the first definition, the informal definition of closure. I hope you understood. That is the purpose. Okay. Let's study reflexive closure of relations. What is reflexive closure of relations? Here the reflexive is the property and a relation is given to you, and we need to find the closure of the relation with respect to reflexive property. So let's see the definition. Reflexive closure of relation. Reflexive closure, what it means? It simply means that you add minimum number of necessary pairs in the relation to obtain the reflexive property. A relation is given to you, and we need to find the reflexive closure. So what we need to do? We need to obtain the reflexive property. So to obtain the reflexive property, we will add minimum number of necessary pairs. The new relation that we will get, that will be called reflexive closure of R. Okay. So this is the definition. You can see, given a relation R, find a reflexive relation containing R that is as small as possible. that will be called reflexive closure of R. Okay, so remember, for any given relation R, what is reflexive closure? Reflexive closure is a reflexive relation containing this relation R, which is as small as possible. So, in other words, you can say that in the relation R, you add minimum number of necessary pairs to obtain the property reflexive property. The new relation will be called closure of relation R with respect to reflexive property, or I can say reflexive closure of R. And this is a note, very important note, that whatever relation you take on any set, the reflexive closure will always exist. I told you, irreflexive closure, anti-symmetric closure, they may or may not exist. Okay, but this reflexive closure will always exist for every relation on any base set. Okay, so read this note. For any relation on any set A, whatever relation you take, basically, the reflexive closure will always exist. It will never happen that reflexive closure does not exist. Reflexive closure will always exist. Okay. Now, how to find the reflexive closure? So, what you will do to find the reflexive closure? You will add only the necessary pairs in R. What are the necessary pairs to bring the reflexive property? Can anyone tell me? To obtain the reflexive property, what are the necessary pairs that I must add in R? What are these necessary pairs? These necessary pairs are the reflexive pairs, yes or no? These are all the reflexive pairs that you already know. Okay, so basically I can say that for any relation R, what will be reflexive closure of R? What will be reflexive closure of R? Reflexive closure of R will be equal to R plus all reflexive pairs. Do you agree? Because to bring the reflexive property, the necessary pairs are the reflexive pairs. So in relation R, you just add all reflexive pairs. That's it. Nothing else you have to do. That's it. This is what you need to do. To find the reflexive closure of R, what you do in the R, you just add all the reflexive pairs. That's it. Nothing else you need to do. Because to bring the reflexive property, what are the necessary pairs? The necessary pairs are the reflexive pairs. So in the relation R, you just add the reflexive pairs. That's it. Do you remember the definition of identity relation? In the previous lecture, we have seen the definition of identity relation, which is also called diagonal relation, which is also called equality relation. In the previous lecture, you can see identity relation definition we have already seen. So this previous lecture you can find on the YouTube. On the YouTube, you can search goclasses inverse relation. Basically, in this lecture, in this previous lecture, we have seen the definition of inverse relation, complementary relation, what is complement of a relation. We have also seen the definition of identity relation. Okay. So in this lecture, we have seen this. So you can search on YouTube, goclasses inverse relation, and you can watch it. So let me repeat, what is the identity relation definition? Another name is diagonal relation or equality relation. So remember, if you have any base set A, if we have any base set A, base set is A, then what is the identity relation on A? Let me write it. So what will be the identity relation or diagonal relation? So what is the identity relation on A? That will be, that you can write using the symbol I, or you can use the symbol delta, or you can use the symbol E, because I told you that identity relation is also called diagonal relation, it is also called equality relation. Okay, so these symbols you can use. And what is this identity relation? This is basically all the reflexive pairs, only the reflexive pairs and all the reflexive pairs. Okay, this is the definition. So please understand that identity relation on a set A, that is set containing all and only the reflexive pairs, means every element is related to itself and only related to itself. You must have all the reflexive pairs and only the reflexive pairs, nothing else. So you can see this is the identity relation. It has all the reflexive pairs A comma A and only the reflexive pairs, means for every element in the base set you put A comma A, then you will get identity relation. So I can say this identity relation, this is the smallest reflexive relation on A. On this base set A, the smallest reflexive relation, that is identity relation. Okay, this is the definition of identity relation. Now you tell me how to find the reflexive closure of a relation. That's very simple. The reflexive closure of a relation, what that will be? Reflexive closure, reflexive closure of R. Okay, what that will be? That will be equal to, in this relation R, you add means union. You do the union with identity relation. That's it. Yes or no? R union with identity relation. That will be your reflexive closure. That's it. Okay, what is this? This is identity relation. So what you do? You just do R union with identity relation. The result will be reflexive closure of R. That's it. Nothing else. Okay. So I can say reflexive closure of R. Okay, this is how you can denote. Here, this R means reflexive. So what is reflexive closure of R? Reflexive closure of R is R union identity relation. This is your answer. And this is the note that for any relation R on any set A, reflexive closure always exists. Tell me the answer for this question. What is the reflexive closure of relation R on set of integers? So the relation R is given to you A comma B, where A is less than B, on integers. On integers. This integers is the base set. Okay. Tell me, this relation R, does it already satisfy reflexive property? No, it does not satisfy reflexive property. What will be reflexive closure? So the reflexive closure R of R. What that means? That means reflexive closure of R. So what the reflexive closure of R? That will be equal to, in this R, you take union with identity relation. What is identity relation? That is A comma A. Okay, where A belongs to the Z means base set. Okay, so when you do R union identity relation, what you will get? Ultimately, what you are going to get. So you can see we have this relation R has pair AB where A is less than B, union with AA. Okay, so finally what we will get? We will get AB such that A is less than or equal to B. Yes or no? Okay, this equal is coming because of identity relation, and this less than is coming because of R, and we are basically taking their union. So finally it will be pair A comma B such that A is less than equal to B. This is the reflexive closure. Is this clear? The reflexive closure will be this relation. This relation is the reflexive closure of this relation. I hope you understood. You can read the explanation here. You can see this is the reflexive closure. A comma B pairs such that A is less than equal to B. So we have seen the concept of reflexive closure. You can read these slides. Everything that is written here, we have already seen. You can see that reflexive closure of R equals to R union delta, where delta is the identity relation, also called diagonal relation. Okay, so this we have already seen. The reflexive closure of R is R union delta. These slides you can read. Yes. Tell me one thing. If graph representation of R is given to you, then how to find the reflexive closure of R? Simple question. If the graph representation of relation R is given to you, and I ask you, find the reflexive closure, then what you will do? Then you will just add the self loops, nothing else. Very good. Just add all the self loops. So you can see that is written here. You can read that add self loops to all the vertices in the graph representation of R. Okay, tell me one thing. If I give you matrix representation of relation R, for relation R, matrix representation is given for the relation R. How to find the reflexive closure? How to find the reflexive closure? To find the reflexive closure, you will add all the reflexive pairs, and you can see this man diagonal. This is the these are the all the reflexive pairs. So to find the reflexive closure from the matrix representation of R, what you will do? You will just make the main diagonal all ones. Yes or no? In the main diagonal, you make all the ones. This main diagonal, you make it all ones. Put ones in the main diagonal. That is what is written here. Put ones on the diagonal of the matrix representation of R. Okay, very easy. So if the graph is given, then also you can find the reflexive closure by adding the self loops to all the vertices. And if the matrix representation is given, then also you can find the reflexive closure by putting ones on the main diagonal. Okay, very simple. So you can read these slides. You can see this slide also you can read. This slide also you can read. Everything that is there in these slides we have already seen. Now let's move on. Let's study symmetric closure of relation. Now the property is symmetric, and we need to find the closure of relations with respect to symmetric property. Let's see the definition. Given a relation R, how to find the symmetric closure of that relation? That is very simple. We will add minimum number of necessary pairs to obtain the symmetric property. This new relation that we get, that will be called symmetric closure of R. So you can read that. What is symmetric closure of R? Given a relation R, the symmetric closure is basically a symmetric relation containing R that is as small as possible. Okay. In other words, given a relation R, the symmetric closure, how to find the symmetric closure? In this relation R, you just add minimum number of necessary pairs to obtain the symmetric property. New relation that you get, that will be symmetric closure of R. And this is the note. For any relation R on any set A, symmetric closure always exists. Remember, symmetric closure will always exist for every relation. Whatever relation you take, symmetric closure will always exist. Okay. Now, given a relation R, how to find its symmetric closure? Can you give me some idea? A relation R is given to you. You want to find the symmetric closure. Means in this relation R, you want to add minimum number of necessary pairs to bring the symmetric property. How to do that? Let's see the idea. Okay, let's see the idea. And from this idea, we will make a formula also. But let's see the idea. See, this relation R, let's assume this relation R contains AB, this pair. Okay, this relation R has this pair AB. Tell me, to bring the symmetric property, to find the symmetric closure, which pair I must add in this relation R? Tell me. This is the relation R which has this pair AB. Okay. To bring this symmetric closure of R, let me write like this. Okay, what this means? This means symmetric closure of R. This means symmetric, and this means relation R. So, if we have this relation R which has this ordered pair AB, then to find the symmetric closure, what we will do? Very good. We will add BA. If AB is there, we will add BA. Okay, this inverse, or I can say converse pair, I will add. Correct? What is this? This is the converse or inverse. This is the converse or inverse of AB. Okay, this is the converse or inverse of AB. So basically what we are doing, we are adding all the inverse pairs. For every pair, we are adding all the inverse pairs. So Are you getting the idea what we are doing? We are taking the union with the inverse relation. To find the symmetric closure of R, what we are doing? We are doing R union R inverse. Do you remember the definition of R inverse? Inverse relation. In the previous lecture, we have already seen. You can see this inverse relation concept. Inverse relation is also called converse relation. It is also called transpose relation. All these are different names for the same concept. Inverse relation concept we have already seen in the previous lecture. You can see inverse relation. You can find this lecture on the YouTube. On YouTube, you can search goclasses inverse relation. So you can see what is this inverse relation. Let me tell you the definition. R inverse for any relation R. How to find the inverse relation? So inverse relation will be basically BA such that AB belongs to R. Means from relation R, if you want to find R inverse, then what you do? Just swap the elements in every ordered pair of R. Simply swap the direction of every ordered pair in R. Means in R, if you have AB, then in R inverse, you will have BA. It's like this. If AB belongs to R, then BA will belong to R inverse. Basically, every ordered pair of R, you just swap the elements of that ordered pair. Okay. This R inverse, this is also called R converse, this is also called R transpose. So all these are different names for the same concept. Okay. So this is what I'm saying here, that to find the symmetric closure of R, you just do R union R inverse. Because if R contains AB, this ordered pair AB, then to find the symmetric closure, you will put BA. What is BA? BA is basically inverse of AB. So what you are doing? You are doing union of R with R inverse. That's it. Okay, so let me write it here. So this is what is written here. You can see the symmetric closure of a relation can be constructed by taking the union of relation with its inverse. Means R union R inverse. That is the symmetric closure of R. Okay, so that's the whole point. Nothing else. Okay. This is what we have seen. So finally, I can say then remember that symmetric closure of R. Symmetric closure of R. To find the symmetric closure of R, what you will do? You will take R union with R inverse. This will give you the symmetric closure of R. Okay. R inverse is also called R transpose. It is also called R converse. Okay. So you can see the symmetric closure of R, that is R union R inverse. I hope you understood. Tell me the answer for this question. What is the symmetric closure of relation R? This relation R is given to you on set of positive integers. So the relation R is AB, where A is greater than B. Means the first element is greater than second element. Okay. On positive integers, Z plus. 0 is neither positive nor negative. Positive integers. What are the positive integers? They start with 1. 1, 2, 3, and so on. Okay. So you tell me, what will be R inverse first of all? What will be R inverse? That's very easy. In this R, what we have ordered pair AB where the first element is greater than second element. If I swap these elements in every ordered pair, if I swap the elements, then what I will get? Then what I will get? Then I will get AB where the the first element will be less than second element. Yes or no? First element will be less than second element. Do you agree with me? Okay. See, very simple point. In this relation R, we have ordered pair AB where first element is greater than second element. It's for example 5, 4. Now, if I swap the elements of 5, 4, what I will get? I will get 4, 5. So now the first element is less than second element. Okay. So if this is the relation R, then the R inverse will be this one. Okay. Very simple. Now you tell me what will be R union R inverse. R union R inverse. If I take the union of these two, you can see if I take the union of these two, then I will have ordered pairs AB such that either the first element is greater than second element or the first element is less than second element. So overall, I can say that first element is not equal to second element. First element is not equal to second element. This is R union R inverse. And this R union R inverse, that is the symmetric closure of R. That is the symmetric closure of R. That's the answer. Okay. So finally, this is the answer. This is the symmetric closure of R. I hope you understood. You can read the explanation here. Tell me the answer for this question. Relation R is given to us on set 1, 2, 3, 4. This 1, 2, 3, 4, this is the base set, and this is the relation R. Find the reflexive closure of R, find the symmetric closure of R. Tell me the reflexive closure of R, what that will be? Let's call it RR and let's call it SR. So tell me the reflexive closure of R, what that will be? You write R as it is. Reflexive closure of R, that is basically R union identity relation. Okay. So you write R as it is. Okay. You take the union of R with identity relation. So only 2, 2 is remaining. Yes or no? Only 2, 2 is remaining. That's it. This is your answer. You can see. Very simple. So this is the reflexive closure of R. What is the symmetric closure of R? That will be R union R inverse. Okay. So the inverse of 1, 1, that will be 1, 1 itself. Yes or no? The inverse of reflexive pair will be that pair itself. So 1, 1, 1, 4, and I should also put 4, 1 because R union R inverse. So I should also put 4, 1. 2, 3, I should also put 3, 2. 3, 1, I should also put 1, 3. Then 3, 3, then 4, 4. Okay, this is the answer. I hope you understood. Simple, right? Tell me the answer for this question. The relation R is given to you in the graph format. In the graph representation, we need to find reflexive closure of R and we need to find symmetric closure of R. Reflexive closure of R you find. This means reflexive closure of R, and also find symmetric closure of R. So what that will be? To find the reflexive closure of R, to find that, what you will do? A, B, C, D. These are the elements. So to find the reflexive closure of R, you draw the R as it is. Okay, draw the R as it is. R as it is you draw. This is the relation R. Now on every vertex, you put the self loop for the reflexive closure. That's it. Very simple. This is the reflexive closure. What will be the symmetric closure of R? You draw R as it is. Draw this relation R as it is. Now what you do? To find the symmetric closure, what you will do? For every direction, for every edge, you will put the edge in the other direction also. So you will put this edge also. Do you agree? This one directional edge, you will make it bidirectional. Basically, make every unidirectional edge into bidirectional. Yes or no? That's it. So tell me a note I want to ask. If the graph representation of R is given to you, then how to find the symmetric closure? Finding symmetric closure. Finding symmetric closure. Finding symmetric closure of R. If graph representation given, then what you will do? Finding symmetric closure of R, graph representation given, then what you will do? And matrix representation given, then what you will do? So tell me, if the graph representation is given, then what are you going to do? Make every unidirectional edge bidirectional. Yes or no? Make every existing edge, make every existing edge bidirectional. That's it. Make every existing edge bidirectional. Okay. What about matrix representation given? Then what I need to do? If matrix representation is given, you already know that I need to do R union R inverse. And if R is represented by matrix M, okay, then R inverse will be represented by which matrix? That will be transpose. Yes or no? The matrix representation of R, if I do the transpose, then I will get matrix representation of R inverse. Okay, so what I need to do? Matrix representation is given, then what I need to do? Then I just need to add, or I can say I need to do this matrix representation of R or matrix representation transpose of R. Okay, just do there or. Means this means union. Basically we are simply doing the union, or I can say or. Is this clear to everyone? Let me know. Just take the transpose and we need to do the union, so you just do the or. Okay, means here what will happen? It's basically like 1 or 1, that will be 1. 0 or 1, that will be 1. 0 or 0, that will be 0. 1 or 0, that will be 1. Okay, this is what it means. Is this clear? I hope you understood. So this is how you can find symmetric closure of R. If graph representation is given, if matrix representation is given, easily you can find the symmetric closure of R. I hope you understood. You can read these slides, which I have taken from various standard resources. Everything that is written in these slides we have already seen. I hope you understood the concept of symmetric closure, reflexive closure. Now we are going to solve all the standard questions from Kenneth Rosen book. So let's solve one by one. Let's solve this question from Kenneth Rosen book. Suppose that relation R is on finite set A is represented by matrix MR. Show that the matrix that represents the reflexive closure of R, that is MR or IN. See, what is this IN? This is the identity matrix. Okay, in the linear algebra, in engineering mathematics, you study something called identity matrix. Do you know what is identity matrix? Identity matrix of size n by n. Okay, so let me tell you what is the identity matrix. See, identity matrix IN. For example, what will be I3? Let me tell you. I3 means 3 by 3 matrix you make, and identity matrix means all the diagonal elements will be 1. Main diagonal element, that will be 1. All the remaining will be 0. Okay, what will be I2? I2 will be main diagonal elements 1 1, all the remaining elements 0 0. Okay, so similarly, what will be IN? IN will be n by n matrix where main diagonal elements will be 1, Okay, all the main diagonal elements are 1, all the remaining elements are 0. Okay, like that. I hope you understood. So this is identity matrix. Now you tell me, if you have matrix representation of R, how to find the reflexive closure of R? Tell me what you will do. That you already know, that if relation R is given to you, given matrix representation of relation R. Okay, matrix representation of relation R is given to you. Then tell me how to find reflexive closure. How to find reflexive closure of R? What you will do? I told you, to find the reflexive closure of R, what you will do? You will make the main diagonal 1. Yes or no? Put ones in the main diagonal. Yes or no? Put ones in main diagonal. By default, diagonal means main diagonal. Okay. So put ones in diagonal of MR. Correct? This is one way. Or what you can do, the same thing in another way. What you can say? The same thing in another way, I can say that same thing in another way. I can say that you are basically doing MR or identity matrix. Yes or no? This is what you are doing. MR or identity matrix, because this identity matrix, what it has? It has ones in the main diagonal and all the remaining cells are 0. So you will just do the OR with identity matrix. Then you will get reflexive closure of R. Okay, this is the answer. That's the same thing the question is asking. You can see, suppose that relation R is represented by matrix, then this matrix will be the reflexive closure of R. Okay, that's it. Very easy. Because if you are putting ones in the main diagonal of MR, that is same as taking OR with identity matrix. Okay, this will be your answer. Simple, right? So very easy. Let's solve question 13 from Kenneth Rosen book. Suppose that relation R on finite set A is represented by matrix MR. Means the relation R is represented by matrix representation. Show that this matrix will be the symmetric closure of R. Tell me how to find the symmetric closure of R. We have already seen that. Symmetric closure of R, if you want to find, then what you will do? You will take the matrix representation of R. You will do OR with matrix representation of R transpose. Okay. Because you can see this MR represents R and this MR transpose represents R inverse, and the symmetric closure of R, that is R union R inverse. Okay, R is represented by MR, so R inverse will be represented by what? That will be represented by MR transpose. Okay, so that's it. So this question number 13 also we have done, that this matrix MR or MR transpose, this will be the symmetric closure of R. Very simple questions. Let's solve question 15 from Kenneth Rosen book. When is it possible to define irreflexive closure of relation R? That is, a relation that contains R and is irreflexive and is contained in every irreflexive relation that contains R. Notice one thing, something interesting. There are two things interesting here. Notice that from here, this is basically the formal definition. Please focus here. This is what I was talking about when I was discussing the formal definition. Notice here, a relation that contains R. See. A relation that contains R. This was our one a relation that contains R is irreflexive. This is our 2, and is contained in every irreflexive relation that contains R. This was our 3. Overall, I can say that it was our 3 number, it was our 2 number, and it was our 1 number. So overall, this 1, 2, 3, if you see this 1, 2, and 3, that is your formal definition of closure. 1 and 2 and 3, that is the formal definition of closure. Okay, so you can see in this question they are basically talking about closure. Okay, now the question is asking, when is it possible to define irreflexive closure? Means when the irreflexive closure will exist. This we have already seen. If the given relation is already irreflexive, then irreflexive closure will exist and the relation itself will be irreflexive closure of itself. But if the given relation is not irreflexive, then you can never find irreflexive closure. Means irreflexive closure does not exist. Yes or no? Okay, see, very simple point. When does irreflexive closure exist? When does irreflexive closure exist? So you just tell me 2 cases I am making and you tell me the answer. When does irreflexive closure exist? You tell me case 1. Case 1 is given relation R is not irreflexive. Now you tell me. Case 1, given relation R is not irreflexive. If the given relation is not irreflexive, means there is some violation of irreflexive property, means R contains some reflexive pair. Now, can you bring the irreflexive property by adding? Then in this case, irreflexive closure does not exist. So this actually we have already seen in this lecture. In the beginning, we have already seen that if the given relation is not irreflexive, means there is some violation of irreflexive property, means R contains some reflexive pair, then you can never create irreflexive closure. Means you can never add something to R to bring the irreflexive property. So I can say if the given relation is not irreflexive, then the irreflexive closure does not exist. Okay, yes or no? Then the irreflexive closure does not exist. And what is the case 2? What is the case 2? Case 2 is given relation is irreflexive. Given relation R is already irreflexive. Now tell me, if the given relation R is already irreflexive, then there is no need of adding any pair to bring the irreflexive property. Means the given relation R itself is the irreflexive closure of itself. Yes or no? So I can say that given relation R is already irreflexive, then R is the irreflexive closure. Then R is the irreflexive closure of itself. That's it. So actually whatever I have written here, we have already understood this in this lecture. In the beginning, we have already understood that if the given relation is already irreflexive, means the property is already satisfied. So there is no need to add any pair to obtain this irreflexive property. So R itself is the irreflexive closure of R. Okay, so that's it. Overall, I can say the question is asking when is it possible to define a reflexive closure of relation R? What will be the answer for this? What will be the answer for this question? The answer will be if and only if R itself R already satisfies irreflexive property. R already is irreflexive. Okay, means when R is already irreflexive, then irreflexive closure you can define, and irreflexive closure will be R itself. Okay, and irreflexive closure irreflexive closure will be equal to R. Okay, that's it. This is the answer. I hope you understood. And the same thing will happen for anti-symmetric closure. The same thing will happen for asymmetric closure. Correct? So tell me the answer for this question. When is it possible to define anti-symmetric closure? The same will happen for irreflexive closure, for anti-symmetric closure, for asymmetric closure. Okay, so I can say for this question, what will be the answer? Basically, similar to what we saw in irreflexive closure. Okay, similar to what we saw in the irreflexive closure. So basically, same happens. Same thing happens, I can say. Same thing happens. Same thing happens for anti-symmetric closure and asymmetric closure. Okay, is this clear? The same thing will happen. What it means? Same thing happens. What it means? It simply means that given R, given relation R, if R already symmetric, anti-symmetric, if R is already anti-symmetric, okay, if the relation R is already anti-symmetric, then what will happen? Then anti-symmetric closure exists. Then anti-symmetric closure exists. Okay, and equal to R. Okay, R itself. Anti-symmetric closure exists, that will be R itself. Okay, and what is the second thing? If R is not anti-symmetric, if R is not anti-symmetric, then I can say then anti-symmetric closure does not exist. Closure does not exist. Okay, does not exist. Very simple. I hope you understood. That's it. So whatever I told you, that is written here. You can see this slide I have taken from a standard resource, a standard university. You can see irreflexive closure, anti-symmetric closure, asymmetric closure. Okay, the same concept basically applies to all these three. If the relation is already irreflexive, then irreflexive closure will exist, and that is R itself. If the given relation is not irreflexive, then irreflexive closure does not exist. And the same thing will happen for the same concept will apply for anti-symmetric, for asymmetric closure also. Okay, so all these slides you can read. This slide also you can read. Remember, the transitive closure we will study in the next lecture. The remaining concepts we have already seen. For example, if the graph representation is given to you for the relation R, then how to find the reflexive closure? You just add the self loops on all the vertices. How to find the symmetric closure? You make all the edges, all the existing edges, you make them bidirectional. Means you add edges in the opposite direction also. If there is a as from A to B, then you put from B to A also. Okay. If the relation is given as a matrix representation, then how to find the reflexive closure? You put one. You put ones in the diagonal. How to find the symmetric closure? You take the transpose and you take the or. Okay, take the transpose and then you take the or. Very simple. Okay. This question 35 from Kenneth Rosen book, this question actually we have already solved. Okay. In this lecture, in the beginning of this lecture, this question 35 we have already solved. Do you remember this question? The relation is given. The same relation we have taken, I think, and this is not reflexive, has odd number of elements. These two properties actually we have already seen. So this question 35, I can say already done. Already done in this lecture. In this lecture itself. Okay, this we have already done in this lecture. In this lecture itself. Okay, if you remember, this relation we have taken, this same relation we have taken, and these properties we have taken is not reflexive, has odd number of elements. So already done. Let's solve question 14 from the Kenneth Rosen book. Show that the closure of a relation R with respect to property P, if it exists, then it is intersection of all the relations with property P that contain R. This is an interesting question. Why this is an interesting question? Because to prove this question 14, we need formal definition. Formal definition is very useful to prove it. And using formal definition, you can prove it within 5 seconds. We are already aware of the formal definition, yes or no? Formal definition we have already seen. What was the formal definition? This was the formal definition that closure of relation R with respect to property P, that is a new relation S with property P that contains R, such that S is subset of every relation with property P that contains R. Okay, then this S will be called closure of R with respect to property P. So this was the formal definition. Now let's see this statement 14. It is saying, show that the closure of relation R with respect to property P, if it exists, then it is intersection of all the relations with property P that contain R. Okay. See, you already know from this formal definition. From this formal definition, you already know that this closure, this is subset of all the relations which have this property P that contain R. Do you agree? This formal definition actually we have already seen, and I told you that closure of R with respect to property P, it is a new relation S. It is a relation S. It is a relation S which has 3 properties. What are the 3 properties? The first property is that S contains R. What is the second property? Tell me. This is the first property. What is the second property? And what is the third property? So the second property was S satisfies P. Okay. And what is the third property? The third property is S is a subset of all relations with 1, 2, which satisfy 1, 2. Okay. And if S is subset of all relations which satisfy these two, if S is subset of all such relations, then if you take the intersection of all such relations, what you will get? Tell me. If S is a subset of all such relations which have 1, 2, then if you take the intersection of all such relations, then what you will get? You will get S itself. This is the question, that the intersection of all relations which have property P that contain R, means all relations which have these two property, all relations with these two property, if you take their intersection, then you will get S, because S is subset of all such relations. That's it. This is the proof. I hope you understood. Did you understand? Let me know. Okay, you can see, because S is subset of all such relations with, from here you can notice, from here you can notice. So I can say, so intersection of all such relations, if I take intersection of, so intersection of all such relations, okay, with 1 comma 2. So intersection of all such relations with 1 comma 2, with 1 and 2, will be S, is S. Okay, I hope you understood. Very simple. Is this clear? So very easy. Okay, or you can make a diagram if you want. I can make a diagram. I told you that if this is our, if this is the relation R, okay, this is our relation R. Okay, okay. Now I told you what is S. S means closure. Okay, what is S? S means closure. So S is the closure. S, this is S, this is S, and to find S, what we will do? We will add only the necessary pairs. These are the minimum number of necessary pairs. These are the minimum number of necessary pairs. Okay. So you can see, because these are the necessary pairs. Now notice, if I make any relation that contains R and that has this property P, then that relation must be a superset of S, because that relation must contain these necessary pairs. Okay, yes or no? If I make any relation if I make which contains R and has this property P, then it will be superset of S, that you already know. Okay, so this will be T. Similarly, maybe I can make another, for example, maybe this will be M. Okay, like that. The whole point is that if you take intersection of S T M, then that will be S. Okay, you can see these are the relations that satisfy relations that satisfy these are the relations that satisfy two properties. What are the two properties? First is they are superset, that first is they that satisfy these two property, that they contain R and satisfy property P. Okay, yes or no? So finally, if I take the intersection of all of them, M intersection T intersection S, then that will be S only. Okay, I hope you understood. Anyway, so basically using the formal definition, you can say this statement. Okay, means you can say that this is another definition of closure property. Basically, closure of a relation with respect to property P, you can say if it exists, then it is basically intersection of all the relations which contain R and which satisfy property P. So please understand that this, you can consider that this is another third definition of closure. You can think of this as, okay, this is like third definition of closure that we have seen. This is like third definition of closure. Okay, I hope you understood. So anyway, to solve the questions, we are never going to use it, but maybe in true false they can ask, right? Yes or no? And this is actually derived from the formal definition. Yes or no? This you can easily prove, or I can say derived. This derived, or I can say proven, derived from formal definition. Okay, so anyway, don't worry about this one. The point is that this you can easily derive from the formal definition. And now I hope you understood that this can work as a third definition of closure. Okay, basically closure of a relation R with respect to property P, that is basically intersection of all the relations that contain R and have property P. Okay, that's it. I hope you understood. This is the last question for this session. For a relation R, are the following always same? First you find reflexive closure, then you find symmetric closure, or first you find symmetric closure, then you find reflexive closure. Will you always get the same answer? Tell me. Let me know. For a relation R, are the following always same? Means you have this relation R, you first find reflexive closure, then you find symmetric closure. And in the second case, you find symmetric closure, then you find reflexive closure. Means symmetric closure, reflexive closure, can you can you find them in any order? First symmetric, then reflexive, or first reflexive, then symmetric? Can you do them in any order? Will you get the same answer? The answer is yes. What is the reason? What is the reason? So the reason is very simple. Tell me. Okay, just tell me. See, reflexive closure and symmetric closure, do they interfere with each other? Think about the graph representation. Use graph representation to prove it. Okay, in your mind, just close your eyes. Think about the graph representation of relation R. For reflexive closure, what you will do? You will make the self loops. For symmetric closure, what you will do? You will make all the edges bidirectional. Do they interfere with each other? No, they don't interfere with with each other, right? Yes or no? Okay. So very simple point, that first, if you are finding the reflexive closure, then it means you are putting all the self loops. Then if you are finding the symmetric closure, notice one thing, that the reverse direction of self loop is itself, means the self loop, if I put in the reverse direction, then that will be same. Yes or no? Self loop is already bidirectional. Self loop is unidirectional or bidirectional? Can anyone tell me? Anyone want to tell me the self loop, is it unidirectional, is it bidirectional? It's both. Okay, it's like, it's like from A to A. So from A to A, so it's already bidirectional. Self loop is already bidirectional. Okay, it's from A to A. So you tell me, for reflexive closure, you will put the self loops, and for symmetric closure, what you will do? If there is any unidirectional edge, you will make it bidirectional. Notice one thing, they do not interfere with each other. Okay, because for a self loop, the bidirectional, that is already bidirectional. So basically, self loop is not disturbed by the symmetric closure. I can say, in simple words, I can say the symmetric closure does not disturb the self loop. This line can I speak? Think about this statement. Can I say that symmetric closure does not disturb the self loop? Yes, symmetric closure does not disturb the self loop. If the self loop is there, it will be there. If that is not there, then it will not be there. Symmetric closure does not disturb the self loop. So overall, I am saying that symmetric closure does not disturb the self loop, and reflexive closure only has self loop, only puts the self loop. So symmetric closure does not disturb self loop, and reflexive closure does not disturb the remaining edges. So they do not interfere with each other. Overall, I can say that you can do them in any order. First you can do reflexive closure, then symmetric closure, or first you can do symmetric closure, then reflexive closure. The result will be same. Okay, so I can say proof number 1, always is always same. Are the following always same? The answer is yes. Okay, and what is the proof 1? I will also give you proof 2. Proof 1, what is the proof 1? Proof 1 is that use graph representation. Okay, use graph representation. You can also use the matrix representation if you want. Use the graph representation, and you can easily see that symmetric closure does not disturb self loops. Symmetric closure doesn't disturb self loops. Okay, And reflexive closure doesn't disturb. Reflexive closure doesn't disturb the remaining edges except self loop. The remaining edges. Okay. So, so they do not interfere with each other. So reflexive closure basically, so they do not interfere with each other. So they do not interfere with each other. Okay. Very simple. Let me also tell you the same thing. You can think from the matrix representation point of view. Tell me one thing. If I take a transpose of any matrix, the man diagonal is disturbed or not? When we take transpose of n by n matrix, you have n by n matrix. I'm talking about n by n matrix. For n by n matrix, if I take the transpose, the man diagonal will be disturbed or not? It will not be disturbed. The same thing. So you can see the symmetric closure will not disturb the man diagonal, and the reflexive closure will not disturb the remaining cells. The reflexive closure will only disturb the man diagonal. It will not disturb the remaining cells. Symmetric closure will not disturb the man diagonal. So they do not interfere with each other. Reflexive closure, symmetric closure, they are not interfering with each other. So you can do them in any order. I hope you understood. Let me give you another proof which I think you will find more interesting. So let me give you another proof. Proof 2. See. If I first take reflexive closure, then I take symmetric closure, then what I will get? You have relation R. First you take reflexive closure, then what you will get? Tell me what you will get. Relation R, first you take reflexive closure, what you will get? You will get R union delta. Did you forget it? R union delta you will get, yes or no? R union identity relation. Okay. Now you take symmetric closure. So what you will get? Remember, the symmetric closure will not disturb this delta. Symmetric closure does not disturb this. Or I can or just okay, think about this as S. Think of this as S. Okay, so symmetric closure will be what? S union S inverse. What that will be? What that will be? That will be R union delta. Union R inverse union delta inverse. What is delta inverse? Delta inverse is same as delta. Yes or no? Because what is delta? Delta is basically identity relation. So if you swap the elements in every ordered pair, then also you will get the same delta. Okay, yes or no? You will find this proof interesting, this proof too, because we are using the concepts here. For relation R, first you find reflexive closure, you will get R union delta. Let's call it S. Then you find the symmetric closure, that will be S union S inverse. So that will be R union delta union R inverse union delta inverse. Delta inverse is same as delta. Delta union delta, that is same as delta. Overall, what you got? You got R union R inverse union delta. Because union is commutative, union is associative. Okay, yes or no? Overall, this is what you will get. Agree? And the same thing you will get if you first do symmetric closure, then you do reflexive closure. Okay. For the relation R, first you do symmetric closure. What you will get? You will get R union R inverse. Now you do reflexive closure. Okay. So to do the reflexive closure, you will just take the union with delta. Okay. Did you notice? This is what you are getting when you are doing the second. Means when you are doing the second, then you are getting this. And the same thing you are getting when you are doing the first. In this first also you are getting the same thing. Okay. Here also you are getting the same thing, that R union R inverse union delta. That's it. Hence proved. So which proof did you like more? The first proof, the second proof? Both are interesting. The first one was intuitive. We were using our intuition that reflexive closure, symmetric closure, they do not interfere with each other. We were using graph representation, we were using matrix representation. Okay, that was our proof number one. And this proof number two, here we are actually using the equations, or I can say the concepts. Okay, so both the proof, did you understand? You can see in this first one also, we are basically getting R union R inverse union delta. In the second one also, we are getting the same R union R inverse union delta. Okay, so both 1 comma 2, they are basically always same. Always same, yes. That's it. Okay, whatever we have seen, that is written here. You can read this screenshot. Okay, whatever I told you, that is written here. You can see ultimately you are getting, basically what you are getting R union R inverse union delta. This is what you are getting whatever you do. First you can do reflexive closure, then symmetric closure, or first you can do symmetric closure, then reflexive closure. Overall the same thing you will get in both the cases. That will be R union R inverse union delta. This is what you will get in both the cases. Okay, so that's it. This is the chapter. So in this lecture we have seen reflexive closure, symmetric closure. We have seen a note about anti-symmetric closure, irreflexive closure, asymmetric closure. Okay, we have seen when the closure does not exist, when the closure will always exist. We have seen the formal definition. We have seen the standard questions from the Kenneth Rosen. We have seen some different type of properties. For example, having odd number of elements, having even number of elements. This type of properties also they can define. So basically, all the possible questions on closure, relations closure, that we have seen all the possible questions. Now, only one topic is remaining. That is transitive closure. Okay, that we will study in the next lecture. So in the next lecture we will study transitive closure. We will see theorems, we will see practice, we will do practice, we will see the proof. So that we will see in the next lecture. Okay, thank you everyone. If you enjoyed this lecture, then let me know in the comments. Please put a comment. Please like this session. Let me know in the comments, did you understand everything? Did you enjoy this lecture? Let me know. Okay, thank you all.